Conservation of momentum is a fundamental law of physics that states that the momentum of a system is constant if there are no external forces acting on the system. This is actually an excerpt from Newton's first law, the law of inertia, where an object at rest stays at rest, or an object that's in motion stays in motion unless acted on by an outside force. In the concept of conservation of momentum, we have a situation where we have a system, and that system can be two objects about to collide with one another. Now, because we're talking about collision, we're talking about motion. We have two objects that are moving towards each other. And when they collide, whatever momentum they had before they collided equals the total momentum of the two objects after they collided. So again, in the conservation of momentum, when you have two objects in an isolated system, the total momentum of the two objects before the collision is equal to the momentum of the two objects after the collision. There are two types of collisions that we're going to be talking about. The first one is elastic collisions, and the second type is inelastic collisions. For this video, we will be talking about elastic collisions in particular. And so an elastic collision happens when you have two objects that are initially separated from each other, but then when they collide, they will bounce away from each other and stay separated. And so let me show you an example of this. So here's the animation of two objects moving towards each other. They collide, they bounce, and stay separated. They go in completely opposite directions afterwards. And so that's what you're seeing here. Now, whatever momentum they had before the collision, that equals the momentum they have after collision. Okay? So in a elastic collision, note that the momentum is conserved. Another thing that you might want to note as well when it comes to elastic collisions is that there is also no net loss of kinetic energy in this system. So as the objects collide with each other, after they collide, there's no loss of speed collectively between the two. The collision is said to be perfectly elastic because no energy has been lost. And so when it comes to elastic collisions, you might need to know this. You need to know that momentum is conserved. In other words, whatever total momentum before collision, that's equal to whatever momentum after collision. But also at the same time, you might want to note that kinetic energy is also conserved. So whatever kinetic energy, whatever total kinetic energy you have before they collided, that equals the kinetic energy after they collided. So there's no loss of speed when the two collides. Okay, the kinetic energy remains consistent all throughout the elastic collision. All right, let's go ahead and talk about the equation that is tied to this concept of elastic collisions. So let me just show you really quick the diagram. So we're going to use an example of two dodgeballs. We'll say that one is quite bigger than the other. We'll label the big dodgeball mass 1. We'll label the small dodgeball mass 2. Now both of them are about to collide with each other. So I'm going to show you that they're going to hit each other in these directions. Now, keep in mind that momentum is a vector quantity. Momentum is a vector quantity. And when we say that they are vector quantities, we're explaining that they both have a magnitude and they are going at a direction. And so we have to take into account that momentum is signified as mass times velocity, where velocity is the vector quantity that we're talking about. You'll notice that in this diagram here, mass 1 is moving at a positive velocity direction because it is moving towards the right. Anything that's going up or the right represents a positive value. And you'll notice that mass 2 is going in the completely opposite direction, so we're going to signify this as a negative velocity direction. So again, anything that's going left or down represents a situation where an object is going in the negative direction. So we do have to factor those values in like that when we do the equation. Now this is before they collided, so this is we're gonna say before collision. This is before the two has collided with each other. We'll also call this the initial situation. Now what happens after collision? Okay, so after they hit each other, bam, you'll notice that the big dodgeball, M1, is now moving in the opposite direction of how he initially started off. So now he's going in the negative V direction, where the small dodgeball goes in the positive V direction. And so this is what happens after collision. And so we'll call this the final situation. The primary thing that you got to know when it comes to defining the difference between elastic versus inelastic collisions is that before collision, the two objects were separated from each other, and after the collision, the two objects still remain separate from each other. Okay? And also note that whatever momentum they have before the collision, that's how much momentum they have after the collision. Now, some of the things that you might also want to note as well, because we're dealing with a elastic collision situation, the two main concepts you need to remember. So an elastic collision, the two main concepts is that, well, for one, total momentum is conserved. So whatever momentum you have initially before collision, that's how much momentum you're going to have collectively after collision. So total momentum is conserved. And also, when this happens, there is no loss of kinetic energy. And so, in other words, we can say kinetic energy is conserved. There is no loss of speed when we're looking at both situations where whatever kinetic energy both of them possess before they collided, that's exactly how much kinetic energy that they'll have after they collided. In other words, we can say that the kinetic energy for both initial and final are conserved. So both the total momentum and the kinetic energy are conserved in a elastic collision. All right, let's go ahead and talk about the math. So the math is quite pretty straightforward. You just need to know how to set it up. So we're going to label the equation in relation to the definition of what it means when we're saying conservation of momentum. So again, the conservation of momentum states that whatever total momentum you have before or initially, that equals the total momentum you have after collision, whatever total momentum you have final. Both situations are equal to each other. So momentum, and the sum of the initial momentum equals the sum of the final momentum. So we can state that the momentum of mass 1 plus the momentum of mass 2, that's what you're seeing here and here, equals the momentum, that's for initial, equals the momentum of the first ball plus the momentum of the second ball after collision. So that's what you're seeing here and here. And so the equation boils down to this. Okay, let's go ahead and break this down even further. So as you well know, momentum equals an object's mass multiplied by the object's velocity. So we can look at this as m1 v1 initial. That's for the mass of the first ball, the big dodgeball, plus m2 v2 initial. That's the momentum of the smaller dodgeball, equals m1 v1 final plus m2 v2 final. And so what we've just explained is the primary equation that you will need to know when we're dealing with elastic collisions. So this is the elastic collision equation.